User-friendly wearable sensor systems could revolutionize medical monitoring and diagnosis. Complex data from vital signs can indicate the presence of disease, but are often non-specific. Thus, we developed an electronic node which can detect complex volatile organic compounds and thereby add specificity to a data stream. We focused on severe Clostridioides difficile infection, which causes about 250,000 hospitalizations and 12,000 deaths in the US each year. The C. diff bacterium, however, is present in about 15% of people and usually causes no problems, so detection of the bacteria alone doesn't make the diagnosis, which usually is made clinically after the onset of severe diarrhea. Because C. diff damages the lining of the large gut, we will use our eNose to detect both C. diff specific compounds and compounds that are absorbed through the damaged gut and subsequently released through the skin. This will enable earlier initiation of treatment and can reduce the burden of C. diff, one of the top 5 infectious disease threats recognized by the CDC.
To address this clinical need, we have created a wireless, battery-free eNose sensor to passively collect the volatile organic compounds that are excreted through the human skin or exhaled breath. The flexible sensor, which is smaller than a US quarter, can be comfortably worn anywhere on the human body like a sticker, integrated with a surgical mask, or clipped to the waist or shirt collar. Unlike sensors that require wired connections or rigid batteries, the sensor is built around an NFC transponder that allows the device to be battery-free, low-cost, and easily connected to the more than 2 billion NFC-enabled smartphones active in the world today.
To smell odors excreted from the human body, the eNose sensor includes an array of conductive polymer filaments. The filament array passively and reversibly interacts with the volatile organic compounds excreted from the human body, allowing the sensor to sample the local environment without requiring power. This is an example of the sensor response or breath print signature of the sensor when exposed to methanol, which is a chemical that is commonly excreted from the body. The breath print signature consists of the resistance of each filament in the array.
The eNose sensor was then validated in a laboratory setting by exposing the sensor to 6 known chemicals that are commonly excreted from the human body. The data was projected into a 3-dimensional space using principal component analysis. A supervised machine learning algorithm was then used to cluster the data. The trained model shown here can then be used to classify any new data points. This approach can also be utilized to discriminate the breath print signatures according to health or disease.
The breath print signature can be read at any time simply by holding an NFC-enabled smartphone next to the sensor. The two-way wireless NFC interface wirelessly transfers power to the eNose sensor. The onboard microcontroller is then used to record the breath print signature. And finally, the breath print signature is wirelessly transferred to the smartphone. This data can be locally stored on the smartphone or uploaded to a secure cloud-based storage. Once a predictive classification model has been trained, the breath print signature will be locally classified on the smartphone to provide near real-time diagnoses and initiate earlier treatment.
Each individual expresses a variable breath print signature, and that varies between activities, situations, and possibly even the time of day. So like other biological data, this intra-individual variability contains an underlying complex structure. Loss of complexity of biological signatures is indicative of a change in health. So using advanced analytics, not only will the excreted chemicals be identified, but so will their variability from hour to hour and day to day to provide a more detailed information regarding the individual's health. Finally, we will be able to link that breath print to other biological rhythms, including their pulse, their respiration, their gait, and even temperature. This will improve both the sensitivity and, importantly, the specificity of diagnostics derived from these wearable sensor systems.
Our wearable eNose sensor provides a path towards a rapid, inexpensive, and non-invasive screening system to detect breath print signatures that are associated with health or disease, creating a disruptive strategy for medical diagnosis. We are currently validating the eNose sensor in an ongoing observational human study at the University of Nebraska Medical Center to confirm the robustness and usability of the eNose sensor in hospitalized patients. These data are collected multiple times per day and will allow us to create a predictive classification model using the data obtained from this study.